Now that we've learned our four methods for solving logarithmic equations, it is time to put those to the test in a variety of problems. In this first one, ln of x equals 12. I have one logarithm, and that's it. I have log equal to something. So let's go ahead and use either L1 or L2 to do this. I'll show you both ways. L1, let's convert forms. This is the natural log, so I can write this as e to the 12 equals x. And we're done. X is already by itself. X is equal to e to the 12. You have to go to the calculator to get the decimal approximation. But as an exact form, we can write this as e to the 12. And honestly, probably e to the 12 is a really big number that would be hard to write down anyway. So we'll just leave it like that. Okay. Or we could have used L2, and I could take my ln of x and my 12 and put them in the exponent of e, like that. If ln of x is equal to 12, then e to the ln of x is equal to e to the 12. Then I can use my inverse property on the left-hand side and say that e to the ln of x is just 12 and leave that as e to the 12. And either way, using L1 and L2, we got to the same answer here. B is another example of a logarithmic equation that has a log and a number. So let's try to use either L1 or L2 on this. Go ahead and pause the video, see if you can use either L1 or L2, whichever method you prefer to get the answer here. I'm going to pause, work through it, and then we'll talk about it. Okay, so go and pause now. Did you get x equals -5? I'm showing two methods here using L1. I've converted into an exponential equation, took my log base 3 and said that would be the same thing as the equation 3 squared equals x minus 4. On the right-hand side, I put the left and right-hand sides of my equations in exponents with 3 as the base, and I equated those. And I used 3 because I was given a log base 3. In either case, I ended up with the same equation over here on my left-hand side. I just get that 9 equals 4 minus x. Over here, we have to maybe do one more step of thinking and saying, well, hey, these are my inverse property, 3 to the log base 3. Those undo each other. And I'm left with 4 minus x equal to 9. Got the same equation there, a linear equation, and I solved that to get x equals -5. When we look at C, this one's a little bit different because I have a bunch of logs here. I have a bunch of logs. Let's try to combine them. And I see on my right-hand side, I am adding logs with the same base. So maybe I can go ahead and combine those using my first law of logs, the multiplication to addition or addition to multiplication rule. So on my right-hand side, I'm going to write this as log base 4 of x minus 1 times x plus 4. And on my left-hand side, I'll get log base 4 of x squared plus 3. That was using L3. I had to combine using my first log law on the right-hand side. Okay, well, now I have log base 4 of something equal to log base 4 of something. I have the same log bases equal, so I can use now L4 and equate the insides. What we are left with here is a quadratic equation. A quadratic equation on the left-hand side, I have x squared. On the right-hand side, I'll have some x squareds when I FOIL that out. So let's work through that. On my left, I'll get x squared plus 3 equals, when I FOIL, I'll get maybe an x squared and then a plus 4x and a minus x. So plus 3x minus 4. And pause this and work through this if you need to take some more time on it. But these are some concepts we've seen before, so I'll go through a little quickly. I'll subtract x squared to get those together. And actually, that ends up canceling out my x squareds. And I'm left with 3 equals 3x minus 4. Fantastic. I've reduced this down to a linear equation because my x squareds canceled out. Let's add 4 to both sides, and I'll get 7 equals 3x. And divide by 3, and I'll get x equals 7 over 3. Let's try D, E, and F. In D, I have a logarithm equal to a number. That's getting a little old hat. In fact, that was the same one as A, so let's skip it. We'll move on. We'll look at E. Here I have 3 plus 4 log of 2x equals 19. And so what I see here is that I've got some numbers adding, I've got some multiplying numbers, but I have one log. So this is almost like log of something equal to a number, one logarithm. But first I need to isolate my logarithm. Let's see, to do that, I'm going to first subtract 3 from both sides. And I will get 4 log of 2x is equal to 16. And then to get log of 2x by itself, I'm going to divide both sides by 4. And I'll get that log of 2x is equal to 4. Now that I've isolated my log, I can reanalyze using my 4 methods, and I see that I have log of something equal to a number. This is the prime candidate to use either methods L1 or L2. If we use L1, we would have 10 to the 4th is equal to 2x, which 10 to the 4th is 10,000 equals 2x. And if I divide it by 2, I'm going to get x equals 5,000. We also could have done this with L2. I will leave that work for you. All right, when I look at f, I see I have 2 logs. I have a log of x plus 2 and a log of x minus 1. And what we're realizing is that I need to combine those somehow to be able to write this with just one log, since I also have some number parts. So let's use law of logs, x plus 2 log x minus 1. I can write that as log of multiplication, x plus 2 x minus 1 equal to 1. And now we need to rethink and say, okay, now I have log of something equal to a number. This is a time to use L1 or L2. I'm going to use L2 and I'll do it over here. You can write this, let's see, my base here is 10. We can write this as 10 to the log of x plus 2 x minus 1 is equals 10 to the 1st. On my left-hand side, I'm going to use that inverse property, and I'm going to have x plus 2 and x minus 1 equal to 10. And this is a quadratic equation. In order to solve a quadratic equation, we usually need to get everything on the same side of the equation, which means first I'm going to FOIL my left-hand side and then subtract 10. So let's see, I FOIL this, I'm going to get an x squared, a minus x, and a plus 2x, so plus x, and then a minus 2. And then I'll subtract 10 and get x squared plus x minus 2 minus 10, so really minus 12. Okay. My favorite method for solving quadratics is just to see if it will factor. So let's see, can I think of anything that multiplies to get negative 12 and adds to 1? Sure can. What about x? Maybe minus 3 and x plus 4. And that gives me the solutions of x equals negative 4 and x equals 3. Again, you could have done this with L1. I did it with L2, this last piece, but we did need to start with L3. We needed to start with using our law of logs there. All right, now that we have solved all of these, I want to go back and talk about something that probably should have talked about on all of these, but I think it's easier to talk about all at once. And we have to pause and maybe remember, recall, what is the domain of any log base 2, log base E, log base 10, anything. The domain of logs, if we think about the graphs, they always look something like this, going through that point, is only 0 to infinity, right? The argument of my log needs to be something that's positive. And so I always have to go, because I have a restricted domain for my log, I need to go check for extraneous solutions. Recall that an extraneous solution is a solution that shows up in the process of solving an equation when we kind of change it from one kind of equation to another, to a new kind of equation that doesn't have domain restrictions anymore. We might get some solutions that are actually not in the domain of my original equation. And so because I have a restricted domain, I have to think about that. You might recall that we've thought about this before in solving rational equations, right? The fractions of exponents, we've had to think about that. When we've had square root equations, any kind of thing that has a restricted domain. Square roots have restricted domains, rational expressions have restricted domains, logarithmic equations have restricted domains. Anytime we have to have a restricted domain, we have to check for extraneous solutions. So what I'm going to go through is for each of my answers, I'm just going to go double check that in the original equation, it would have been okay to plug my answer in. So I'm going to check it over here. So I got that x was e to the 12, and e to the 12, I don't know what it is. It's a big number, but it's positive. It's greater than 0. So I can do that. I can plug that into my ln. So yay, it's a good answer. Okay, I'm going to check it for my next equation here. I got that x equals -5, and I'm just going to go double check that I could have plugged -5 into this. So let's see, I have log base 3 of 4 minus -5, which is log base 3 of 4 plus 5, which is log base 3 of 9. Which, now that I see that inside is a positive number, that's all I really need to think. I say, yep, that works. Let's check it in the third one. Here I have 3 logs, so I need to make sure that for all 3 of those, the argument would have been something positive. So let's see. Log base 4 of x squared plus 3 would be 7/3 squared plus 3. And I'm going to go ahead and stop because 7/3 squared, that's positive, and 3 is positive. So my inside is positive. So we're good to go there. Okay, what about x minus 1? I had log base 4 of x minus 1, 7/3 minus 1. 7/3 minus 1, 7/3 minus 1. That inside is positive. So that log is fine to do. And my last one, I had log base 4 of x plus 4. And if I replace that x with 7/3, 7/3 plus 4, yeah, that's a positive number. I can take the log of it. That's allowed. It's in the domain. So that means that this answer is good to go. We'll check on E as well. I got that my answer was 5,000. If I plug 2 times 5,000 into a log, I get 10,000, and I can do the log of 10,000, no problem. That's a positive number. I can calculate that log. The inside is a positive number. Cool. That answer is good to go. And now let's check it for this bottom one here, and I'll do it down here because I'm out of space on that right-hand side. I need to check for each of my x values that they work in both logs. So let's do 3 first. Log of 3 plus 2. Yep, that gets 5. 5 is a positive number, which means is in the domain. That's good to go. And log of 3 minus 1. I'm checking my other log here. 3 minus 1 is 2. 2 is a positive number, so it can be the argument of a log. It's good to go. So that tells me that my solution of 3 is fine. I also need to go check with that -4. And let's see, log of -4 plus 2 is log of -2. Oh no, that's a negative number on the inside of my log. I cannot have a -2 on the inside of a log, which means that -4 cannot be my answer. 3 is the only answer here. The -4 is an extraneous solution. It showed up as a solution to this quadratic equation, but -4 is not a solution to the original logarithmic equation because -4 is not in the domain of my original expression. I cannot have -4 because -4 plus 2 is something negative. So that was an example of all of these methods kind of in practice in a couple of different equations, and then also checking for extraneous solutions. So I want you to be really careful as we go through these, that you're always checking your solutions to see if they're extraneous or not, by just checking if you can go plug that x value back into the log and get an argument that is positive.